Okay, so for today, we're just going to look at an example of an experiment that could be used to kind of analyze magnetic fields and current carrying conductors that are traveling through them. So this would be the type of lab that would have been awesome to do in class, but instead we'll kind of take a look at some of the data here that we could have generated, and then how we would analyze that with, you guessed it, graphical analysis, okay? So a group of students conduct a lab to determine the magnetic field strength of a magnet. So what are we looking for? B, right? That's what we want to know. The students place a wire of length 78 centimeters across a conducting stand fixed to a digital weigh scale, which is insulated from the stand, and then a current is passed through the wire, which results in different readings on the scale. Okay, cool. So let's just take a look at our data here for a sec to kind of think about what's going on. Okay, so here's our setup. Now it's saying that when the current increases, notice that the mass readout decreases. Okay, and it tells us the apparatus is zeroed to negate the mass of the conducting stand. So not the wire, just the conducting stand. So what do you think the mass of the wire is? Well, when there's no current, which means there's no magnetic force being produced, right? Clearly, the mass readout of the wire is 5 grams. Now, what happens as we increase the current? Well, the mass readout decreases. Of course, the mass of the wire isn't decreasing, right? What is decreasing is the net force pushing down on the scale so that it gets a smaller and smaller mass reading, okay? So thinking about that, which way must our magnetic force be going? Well, if it's going to decrease the net force downward, it must be acting against gravity upward, right? So Fm must look like that when it's applied. Okay, so using that information, take a quick look and let's think about it. If you have a magnetic field coming this way and the resulting magnetic force needs to be up, by the way, it might not be super clear. This is kind of coming out of the page a little bit, right? Sort of towards you. If your eye was down here looking, if your eye was looking this way, it would be coming at you, right? If the wire looked flat. In fact, let's just simplify. If we have our wire here, magnetic field, if we're looking at it from the side so that the magnetic force truly is straight up, then the magnetic field would be coming at us. And so with that orientation, which way is current flowing? Current, I said. So take your right hand, okay, point the fingers towards your face because that's the magnetic field. And we know that the magnetic force needs to be up, so it looks like current must be flowing that way through the wire, okay? So from this point of view, that makes this must be the positive terminal, right? Positive terminal, a positive charge like current would leave, okay, would go through the wire like this to produce an upward magnetic force if the magnetic field's coming that way, doop, 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 and then I would continue along that way. Okay, so that makes that the positive terminal. That makes that the negative terminal. If you want to check your work with your left-hand rule, try flipping it around and see if electrons flow this way through the wire. Do you still get the same result? You should. Okay, so see, now we've just kind of worked out what is going on here, right? If as the current increases, the mass readout is decreasing, well, that means the net force downward, which when there's no current, the net force is the force of gravity, right? But as Fm is increased by increasing the current, we are clearly fighting gravity with our magnetic force, not helping it, or else the mass readout would be getting larger. Okay, wrapped our heads around the experiment a bit. Now it just wants us to consider our experimental design, okay? So going through these, we have to decide the numbers of the variables above, which represent a controlled, manipulated, and responding variable R blank, blank, and blank. So these are pulled from a diploma. You can probably tell, okay? It's a good thing to look at these because students often think there's one right answer and panic. There are actually questions on the diploma for numeric where there will be many answers that are taken as correct, okay? So let's first just actually go through here and label each type of variable. So the mass of the wire, do we need to control that? If we use a different mass wire every time, is our experiment fine? Well, no, right? Because we're basing all of this on the mass of the wire initially when it's calibrated to that mass readout. So definitely we would need to control the mass of wire. We can't use a different mass of wire every time. Okay, what about the readout of the mass from the digital weigh scale? What is that? Is that controlled, manipulated, or responding? Well, that's the result we're trying to see, right? We're saying, okay, is it directly what we're interested in? No, really what we're interested in is the force, but this is the responding variable that is going to allow us to think about the force. Okay, so that is definitely the responding variable. This is what we would actually sometimes call our direct responding variable. So this is the thing that we're actually going to measure. Our indirect responding variable would be the gravitational force that that mass readout implies. Okay, but the direct responding variable is the readout itself. Okay, the length of the wire, what is that going to be? Well, if we're looking at, we're changing current, right? We're getting a mass readout. The length of the wire, if we change that, that's going to change the magnetic force. And then we will have two variables influencing our mass readout, and we won't know which one actually caused it, right? So the length of the wire, that must be controlled, okay? Important thing to remember, if you ever have two manipulated variables, guess what? You're not doing one experiment anymore. You're doing two, which is bad science. You don't do two experiments at once, right? You do one experiment at a time. You manipulate one variable and look for a response. So we cannot manipulate the length of the wire. That's in a different experiment if we do that. Okay, the current. So there we go. That's what we're manipulating, right? We're increasing the current and seeing the response in the mass readout. So current would be our manipulated variable. And there better only be one manipulated variable, or this is not a good experiment. Okay, so the force of gravity, right? We are not manipulating the force of gravity. That should actually stay the same the whole time. Why? Because are we changing the mass? No. If we did, right, then that would mean this was not a controlled variable, obviously. If we change the mass, that's the only way to change the force of gravity. So the force of gravity is actually going to change stay the same the whole time. It's the force net that's going to change because of the magnetic force that we're going to introduce that's going to fight against it. Which, okay, there we go. The force of magnetism. What is that? Well, this would be our indirect responding variable, right? As we change the current, we're going to see a different mass readout, which was our direct response, right? But why did we care about that direct response? Because we were trying to see what is the force of magnetism that is being produced by that change in current. So this is the responding variable. You could say indirect, because we're not directly measuring that. We're going to have to calculate it. But this we are directly measuring, right? This is data from our thing that even before doing any analysis, we can say that's the response. So for your controlled, manipulated, responding, any of these would be taken as correct. You could have said for controlled, either 1 or 3 or 5. Manipulated, you could have said 4 and nothing else. You better only have one manipulated, right? For responding, truthfully, you only have kind of one response that you're interested in. However, that might be measured directly or indirectly, right? So for example, in this one, we directly get the response as the readout of the mass on the digital scale. But what are we really interested in based on that is the force of magnetism that would imply, right? It's like saying, okay, we want to see our response in the rate of photosynthesis. How are you going to do that? Well, you're going to measure the amount of oxygen produced by a plant. Okay, so directly you're measuring the amount of oxygen, and then you're using that to really measure the rate of photosynthesis. All right, so then these students plotted their data. They did mass readout versus current. So the mass readout versus the current. So what's step one of any kind of graphical analysis? You need a line of best fit. Okay, so there's the line of best fit I drew. Yours might be slightly different, but it shouldn't be too far off. Okay, now what are we going to use this line of best fit for? Are we going to find the area underneath it? Are we going to find an intercept? Are we going to use the slope? Well, we actually have a couple options here. I'm going to show you both. Okay, now don't forget, what are we looking for here? We're trying to figure out the magnetic field strength. So let's think about what we have that relates these kind of variables. So mass readout. What is the mass readout? What is that really telling you? Well, it's the net force, right? If we're saying, okay, when there's no current, there's no FM, and so Fg is the net force, and so that's just the force of gravity, the weight of the wire, right? As we increase, the net force gets smaller, and so the mass readout gets smaller because FM is kind of pushing this wire upward a bit, right? So that's what's going on there. So really, what are we looking at here? We're saying, well, our kind of equation, our kind of starting point is going to be, or at least for this way, it's going to be F net equals the magnetic force plus the force of gravity. Okay, great. So how is F net kind of being determined here? Well, we're saying that the scale is reading out some mass based on what it feels, right? Remember, scales don't truly measure mass, right? Scales measure weight, and then they do a little calculation. They divide by 9.81, and they say, okay, here's your mass, right? If you take a scale to another planet, it doesn't work anymore because scales are calibrated to work on Earth's gravity, right? So what is F net really doing? What is the scale telling us? It's telling us the force that it totally feels. And it's saying, okay, I'm feeling a force as if this mass were on me. The readout mass times G, right? It's saying, seems like there's something with this much mass on me. We know the wire has more mass than that, right? But the scale doesn't know that. It's just saying, here's what I feel because the magnetic force is taking away a bit of the weight, okay? So M readout times G. Let's just go ahead and simplify that to MR, okay? MRG, okay? Equals the magnetic force. Well, we know the magnetic force is current times the perpendicular length of the wire times the magnetic field strength. Hey, that's what we want in the end. Okay, plus Fg. Now, what is Fg? Well, Fg is the force of gravity that the wire truly feels, right? So this is the force of gravity that the wire actually has, which is what we were saying here. We were saying that the readout of the scale is going to be equal to the kind of the force of gravity that the wire would feel. So wire feels this no matter what, right? This is the force of gravity that the wire is feeling because of its mass. It's just that the net force on the scale is going to get smaller as Fm gets bigger as we increase the current, okay? So how do we get that Fg of the wire? Well, it would be plus m times the wire, the mass of the wire, times G. Okay, just another thing we can think about really quickly here to get a even firmer grasp on what this experiment is saying. Let's just think about it. Does this check out? What if the current is 0? Well, then this whole thing is 0, right? Okay, now we're saying from that we would have that mRg equals m wire times G, right? So if I divide both sides by G, we're saying that the mass readout on the scale would just be equal to the mass of the wire. Well, that makes sense, right? If there's no current and there's no magnetic force, this does make sense. So just always a good idea as you're going through an equation, through an experiment scenario, whatever, just you don't have to just blindly put in the numbers and follow the formulas, right? You can kind of think about it as you go. Does it check out with what your understanding of the scenario would be? Okay, so are we starting to get somewhere here? Well, sort of, okay? It might look hopeless right now, but think about this in terms of a graphical analysis, okay? Notice we have our y variable, the mass readout, okay, is equal to, hey, I, that's our x, so we have a yg, right? Y times something is equal to, okay, x times something plus something. That's starting to sound a little bit familiar. Well, this is starting to look like an equation in the form y equals mx plus b. There's just one thing in the way, the g. If the g wasn't there, we would have something y equals mx plus b, right? We would just have, to have y equals mx plus b, we have to have y by itself, obviously. So let's just go ahead and divide everything by g, and then we'll have y equals mx plus b. And look at that, we even get rid of that there. Okay, so we have y, the mass readout, is equal to x times some stuff, so that plus m wire. Okay, look at this. Wow. So here we have our y, right? That's our y. This is our x. So what's this whole thing that x is getting multiplied by? That whole thing then is m, slope, plus b, the y-intercept. So y equals mx plus b. So that means our slope, the slope of this line, m, okay, so slope equals the perpendicular length times the magnetic field strength over acceleration due to gravity. Look at that. We can find the slope of the line. Hey, we know g, it's 9.81. Hey, we know the length of the wire. That was a constant. So we have then that our required variable, the magnetic field strength, is equal to, solving this for what we want, right? If I multiply by g over L perpendicular, okay, I have that the magnetic field strength is equal to the slope times g over L perpendicular. There we go. Now all I got to do is find the slope, and we're laughing. So just really comes down to finding some good points, right? Okay, so you find two good points that are right on the line or right in the halfway. That one looks pretty good there, right? It's right on that one, right on that one. And then honestly, look at our y-intercept. That is also pretty good. Okay, now remember, I can't just use it because there's a data point there, But if my line of best fit does go directly through a nice little point, well, then I'm allowed to use it. So my line of best fit does. Maybe yours doesn't, but just find another point that does. Okay, so those are going to be my 2 points. So let's first find our rise. We rise from, well, we actually are going to have a negative rise here. Just keep in mind when we go to actually find our magnetic field strength, since we're finding the magnitude, we won't really use those negatives. But our rise, we could say, would still be, looks like 3 grams minus 5 grams, which equals negative 2 grams. Okay. Our run, we go from 0 to 2.246. So our run is 2.6 amperes minus 0 amperes. Our run is 2.6 amperes. Great. Okay, cool. So back to our equation. Now that we've got our rise and our run, again, we're not going to use that negative just because we're looking for the magnitude of the magnetic field here, right? We can't really pull a negative out and say what that means anyway, because the magnetic field is going to be perpendicular to the force. So we're working in a totally different axis here. A negative is actually not going to tell us anything useful. We got to interpret the direction of the magnetic field based on the scenario. So rise over run. Okay, so magnetic field strength then equals, rise is, what did we say? So rise is, be careful, right? It was 2 grams, but these are both going to be in standard units, so does that need to be too. So 2 grams, yes, but that's 0.02002 kilograms. Over our run was 2.6 amps multiplied by G, which is 9.81 newtons per kilogram. We're divided by the perpendicular length, which is, we were told, 0.78 meters, right? They told us the wire that was going through the magnetic field was 78 centimeters. So when I did all that, I got that the magnetic field strength was equal to 0.00967 Tesla, or to 2 sig digs, 9.7 times 10 to the negative 3 Tesla. Okay, so graphical analysis to get the magnetic field strength using y equals mx plus b form. Not always the way we do it, but sometimes it is the best way to do it, okay? So remember, okay, so don't forget y equals mx plus b, a perfectly valid way to analyze a problem. Okay, especially on a graphical analysis question where sometimes we can kind of get away from the equation. We start thinking in terms of slopes and rises and runs. Let's just be careful and do a unit check, okay? So I'll do it off to the side here where I have some room. Free way to check your work. It's a powerful thing. We have kilograms, okay, times newtons per kilogram. Kilograms times newtons per kilogram divided by amps times meters. We want Teslas. Remember, Teslas are a kilogram per coulomb second. Okay, is it equal? That's what we're trying to see. So kilograms times newtons per kilogram, that one's pretty straightforward. Kilograms times newtons per kilogram, the kilograms are gone. Then we've got newtons over amp meters. So we're probably going to have to break down newtons into kilogram meter per second squared over amps times meters. Remember, what's an amp really? It's a coulomb per second times a meter. Okay, so looking at this, we've got meters, those cancel. Okay, so we're dividing by coulombs per second. Dividing by a fraction is the same as multiplying by the reciprocal. So let's just do that to make this a little bit nicer to look at. So we've got kilograms per second squared. That's our numerator. And then once we divide by that fraction, which is the same as multiplying by seconds per coulomb, right? Dividing by a fraction is the same as multiplying by the reciprocal. And so let's look at this cancellation. Oh, this is looking good. Seconds over seconds squared. See ya. Okay, and that leaves us with kilograms per coulomb second equals a Tesla. Very good. We are good. Unit check, had our back. Now, like I said, there's actually kind of another approach we could have taken here. So once we have the y equals mx plus b, once we've got that, okay, we could pop out and do this. We could have taken a different turn here. And what I mean by that is, what if we had used the x-intercept? We can't use the y-intercept, because if we use the y-intercept, then x is 0, and this whole thing goes to 0, right? And then that gets rid of the thing we're looking for. But what if we had used the x-intercept? So I'm just going to kind of pop over here and say option 2. And I'm doing it up here at this part of the page, because this is where we would branch off to option 2. So there's option 1, slope, okay? There's also option 2, the x-intercept. So the x-intercept is the point at which y is 0, okay? So again, now we've got our y equals mx plus b. We've got mr equals ILB over g plus the mass of the wire. Okay, again, so this is y equals mx plus b. At the x-intercept, at any x-intercept, what are your points? Well, they are y at any x-intercept. That's where it crosses the x-axis. No matter what, the y-coordinate is 0, right? That's kind of the definition of where the x-intercept is. However, our x value is what is interesting. So we have, so our y and mass of the readout will be 0, okay? X-intercept, just a reminder, always occurs at x, 0. So we're going to have 0 equals mx plus b, right? We're going to have 0 equals, I'm just going to rewrite this so it looks like mx, right? M times x plus b, mass of the wire. B being y-intercept, not magnetic field, okay? Now, why did I write it like this? Well, now look, we can figure out what our x-intercept is just by reading it off the graph. So looking at this one, it looks like to me about, okay, so this is 6.2, 6.4, and it's about halfway to 6.6. So this is the point, 6.5 amps and 0 grams on the mass readout, okay? So 6.5 amps. So we have that. 0 is equal to the length of the wire times the magnetic field strength over gravitational field times, now we have a point. We have an x. It's 6.5 amps, right? At that point, 6.24, yeah, 6.5 amps. Plus the mass of the wire. Well, how do we get the mass of the wire? Remember, it's y equals mx plus b. So the mass of the wire is 5 grams, our y-intercept, right? Our y-intercept is, at this point, okay, it is 0 amps and 5 grams, the mass readout when we have no current flowing. That makes sense. That's just the mass of the wire, okay? Plus, so 5 grams is 0.005 kilograms. Now all we need to do is just solve this thing for B, because we know L and we know G, right? We know L and we know G. Those are givens. Manipulating it around, we would get that negative 0.005 kilograms, right, is equal to LB over G times 6.5 amps. Now we can, I'm going to go ahead and do this all in one step. I'm going to multiply by G to get rid of that in the denominator, and then I'm going to divide by L perpendicular times 6.5 amps. Just doing that to both sides. Okay, you end up getting that the magnetic field strength is equal to 0.005 kilograms. Again, just dropping that negative here. If we were subtracting it, that would be different, but since we're just multiplying it by, we don't have a negative magnetic field. That wouldn't make any sense. Times the gravitational field strength, all divided by the perpendicular length, and 6.5 amps, which, plugging everything in, over 0.78 meters times 6.5 amps. Realistically, I know this seems a bit weird because you're used to just manipulating the variables, not putting the numbers in. You could have done that. I just started with some numbers put in because we are looking at the intercept. So I just wanted to show you if we put the intercept in, then we can make this 0, right? And then we can treat this. Although there would have been nothing wrong with manipulating it around the other way and then making whatever 0. I'm just doing it this way to make it clear that, okay, we're using the x-intercept. Okay, and when I did it that way, I got that the magnetic field strength is 0.00967.5. So it actually agrees down to the millionth place. Okay, so pretty very similar results. So good. Okay, so or magnetic field strength equals 9.7 times 10 to the negative 3 Tesla. Very similar results using both methods. So one putting it in y equals mx plus b and then looking at the slope. The other one putting it in y equals mx plus b and then saying, okay, what about at the x-intercept where y is 0 and x is some value we can just read off the graph. Okay, so if you're wanting to practice from the formative work, you should now be able to tackle all of 12.3.